Hey, it's Mr. K doing a problem for AP Physics 2. This is one that's going to be based off of an actual AP problem. It's going to be a thermodynamics problem. And what we have here is we have a hot plate, and it's boiling some water, and on top of that is like a plastic lid, and on top of that is going to be a block of ice. And our job is to find out the thermal conductivity of the plastic, and that's going to be a property of the material. And what that is it allows heat to flow through it at a certain rate based upon the property of the material, how thick it is, and how big it is. So, consider a window. The thermal conductivity of the window is based upon the thickness of the window, and maybe you have like double pane windows or these double thickness windows that would prevent the flow of heat into or out of the house, and that's good. It's insulative. But then maybe you talk about, let's say, like a cast iron pot, and the bottom of that is sitting on the stove. Well, the thinner it is, the more heat is going to travel through a bit faster, whereas the thicker it is, it's going to take a little bit more time for that heat to travel through because those molecules need to vibrate and vibrate the ones on top of them, and it just takes a little bit of time for it to travel. So there's an equation for thermal conductivity, which is going to be right here, and all this says is the heat that flows per time is equal to this value K, which is the specific material thermal conductivity, so that's going to change per material. But then it's also based on the difference in temperature. Obviously the bigger difference in temperature, the more heat will flow per second. You touch a hot stove, you burn your finger real fast. You touch a cold stove, that's not going to transfer that much heat to your finger very fast. It might even transfer it away. The area in contact, and then L is going to be the thickness of that thing that's in contact. So, if you have something that's really thick and insulative, then it's not going to transfer heat very fast because as L gets bigger and bigger and bigger, it's going to make the equation smaller and smaller and smaller. So let's get started. We've got a question that says, all right, we've got some students. They do an experiment where they have this setup and they stack plastic plates, and as they stack the plastic plates, they measure the energy flow as more plates are added. And they find that as these plates get thicker, then the energy flow goes down. And their question is, what is the thermal conductivity of the plastic? And so we have these values of joules per second, and we have the value of the plastic thickness. So at the moment with our equation, we have this, and we have this. All right, so we have L and we have Q over T. So if we're going to graph that out, what would be a great thing to graph if we wanted to find K? All right, so the first thing that we usually do whenever we do this whole linearization to find an unknown value is we would move everything but the value that we want, that K value, to the other side. So we have this Q divided by T, which is the data we have here. We can move the L to the other side, and we're going to have the A and the T, delta T, temperature on the bottom here, and that should equal K. Okay, so what information do we already have? So it gives us the area of each of these plastic plates. Those are going to be constant, so that's a constant. The difference in temperature. Well, if we have boiling water, then we know the boiling water is going to be at a constant temperature of 100 degrees Celsius. And the ice, if it's ice, should be at 0 degrees Celsius, and it's melting. It's going to melt into this bucket here. And so our difference in temperature, that's also constant. It's going to stay a constant 100 degrees. So really, our two options as far as graphing things are going to be Q over T, which is going to be this top row, and L, which is this bottom row. And we need to get something that would give us K. So I'm kind of looking for a slope here, and remember that slope is equal to a rise over a run, so something divided by something else. And we could have, well, let's see, if we put Q over T and we divide that by L, that does not give us what we want here, but if we divide it by 1 over L, then that should, right? That should work out. So what I'm going to do is I'm going to graph Q over T divided by 1 over L. So over here, these are going to be Q over T values, and I've already had it kind of scaled out because I knew what these numbers were. And then I'm going to graph out 1 over L. Now, yeah, it was already pre-planned, so you got me. So 1 over L. But I do not have, and this is L, I do not have a 1 over L row. So let me go ahead and do 1 over L, which means I'm going to take all these values and I'm going to divide 1 over the value. So let's just do it here. 1 divided by 0.01 gives me 100. 1 divided by 0.02 gives me 50. 1 divided by 0.03 gives me 33.33. Mr. K, why are you doing that? Because I want to. Leave me alone. 1 divided by 0.04, 25. And 1 divided by 0.05 is going to be 20. Alright, so we've got our numbers there. Very little mental power left. It's late at night. So what I need to do is I need to graph that out. So the first value is going to be 100 on the x, or the horizontal, and it's going to go back to 97 on the y. So 100 on the x, it's going to be 97, so it's going to be somewhere around right up here. I got 50 and 53, and that's going to be somewhere right around there. 33.3 and let's see, 25. So 30, this is 30, 33.3, this is going to be 20, this is going to be 30, this is going to be 35 right there. And 20 on the horizontal and 18 on the vertical, so it's going to be just under right there. So do we have a line that we can linearize? And that's sort of straight. So let's see. Line of best fit, something like that, sucker. And yeah, that should be okay. I'm ignoring these lines that I already, or these dots that I already have. I'm gonna pick this point way over here because I know that's gonna be 100 on the vertical, and that's gonna be 110 right here. So that's just under 100. Let's call it 107. So my rise for this is gonna be 100 and, or just 100. And my run is going to be 107, and that should equal Q over delta T times L. Because 1 over L, if we divide by 1 over L, it's just multiplying by L. So what, should I put that in? I'm just going to leave it. So I need this. We're going to use it right here. All right, we need to use it for Q over T times L. So the thermal conductivity, we rearranged it. And we got Q divided by time is going to be multiplied by L over the area times the change in temperature. Q over T times L, that's this stuff. It's going to be 100 divided by 107. All right, so we've taken care of these three things here already. We need to take the last thing, the area, which is 0.025 from a diagram. And we also need to take 100, because that's our change in temperature on the bottom. This should equal our thermal conductivity K. So let's see, 100 on top, divided by all the stuff on the bottom, 107 times 0.025 times 100, and that gives me a thermal conductivity of 0.3738. And so based upon the area, or based upon the thickness really, 0.3738, and let's see, I'm kind of curious about the units for that. So all I'm going to do is I'm going to look at the units for all this. Let's see what the units have to be. So Q is going to be joules, T is going to be time, so seconds, L is going to be length, so the thickness, A is going to be an area, so m squared, and T is going to be a change in temperature. Here we're using degrees Celsius. So we've got m canceling out with one of those m's. So we've got a thermal conductivity is joules per second degrees Celsius. All right, so those will be the units here. Joules per second degrees Celsius on the bottom. All right, so other questions that the problem asks, this is an actual AP problem. It says, first of all, the students want to create a graph and yield a straight line whose slope, because we did that part. Let's see, on the grid, blah, 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 do the plot, do the plot, do the plot, do the scaling. Next, it says, indicate one potential problem with the setup that could lead to an experimental value for the conductivity that is different than the actual value. Use physics principles. So, what could change our thermal conductivity? And for that, we know the heat here is flowing up from the hot plate into the boiling water, which is going into the plastic, which is going into the ice. What could the issue be that we could foresee in this setup? And I think the real issue would be the surrounding air. The heat's not just going to go from here to there to there to there. The heat would actually go from here to the plastic, and the plastic could lose some amount of heat to the surroundings. And so the heat that the ice would get would not be the same amount of heat that was inputted from the hot plate to the boiling water. Plus the boiling water is boiling, so you're going to have that phase change energy too. Says something about some plastic slab diagram, draw a single arrow representing the direction of heat. Well, that way. Up and out. And describe what occurs in the plastic at the microscopic level that explains the energy flow you indicated in part C. Well, I mean, we always talk about this, and we do it with the box of tennis balls. But if we had this plastic slab here, and we talked about the actual molecules going on, what happens as they heat up? And so here they are. As they heat up, who's going to heat up first? So it's going to be the bottom guys. So these guys are going to start to move around, vibrate around, and as they jostle around because they're getting that extra heat, that heat energy is going to give them motion. Then they will vibrate. The ones that are on top of them will vibrate, and the energy is going to transfer. So this question was that's alright. There's a little bit more to it. It talks about a plastic slab and the wood surface. You touch the plastic slab and you touch the wood. What feels colder? What feels warmer? Well, it's the one with the greater thermal conductivity will feel colder if the room is colder. It's just going to move the heat away from you faster. So thermal conductivity. There might be a question on the AP test. Probably multiple choice question. This was one of the rare free response questions, and we will stop the video here.